Hello, my good people. Welcome again to my YouTube channel, Older V Structural Hub. This is a place where you learn, build, and innovate. And if you are not part of this family, please subscribe and hit that notification bell so that you can be the first person to be notified when a video is uploaded on my channel. Today I want to talk about a new topic, which is moment distribution method. So moment distribution method is one of the methods that is used to analyze statically indeterminate structures. And what are statically indeterminate structures? Statically indeterminate structures are structures whereby you cannot analyze using the three equations of equilibrium. And what are the three equations of equilibrium? Number one, summation of moments about a point is equal to 0. And number two, summation of all vertical forces is equal to 0. And number three, summation of all horizontal forces is equal to 0. Now, let's moment distribution method. So moment distribution is a structural analysis techniques developed by Hadikos in 1930s. It is used to analyze statically indeterminate beams and frames. The method is based on idea of balancing moment at the joint through an iterative process. By distributing and redistributing unbalanced across connected members until equilibrium is achieved, then the internal moment can be determined. So under this, I will make a summary on the formulas and sign convention to be used when dealing with moment distribution method. So let's begin by sign convention. So number one, all the clockwise moment at the end are taken as positive. And then number two, all anti-clockwise moment at the end are taken as negative. So that is all about sign convention. Again, we have terminologies. Terminology number one, carry over factor. This is the ratio of moment produced at the joint to the moment applied at other joint without displaying it. Then you have number two, stiffness factor. So this is the symbol for stiffness factor, which is K. So this is the moment required to rotate the end while acting on it through an angle without translation of the far end. This depends on the nature or type of the beam. So we have two cases whereby case number one, when a beam is fixed end. So case number one is fixed end or a continuous beam. So for this one, K is equal to I over L or 4EI over L. The I is the second moment of area or a second moment of inertia, and the L is the length. The E is the modulus of elasticity. So for case number two, simply supported end or overhanging beam, stock pinned. So K, which is stiffness factor, is equal to 3 over 4 multiplied by EI over L or 3EI over L. Terminology number three, that is distribution factors or DF. These depend on the stiffness factors and it is the moment applied to a structural joint to produce a rotation without the translation of its members. So the moment is distributed among all to the connected members of the joint in the proportion of their stiffness. And then you go to number four, which is fixing moments. It depends on the nature of loading of a beam as illustrated below. So case number 1, as you can see, this is a fixed beam and it is loaded at the center with a loading W, and then we have the moment going in the clockwise direction. So this is clockwise direction, and then moment at A in anti-clockwise direction, and the length L. So fixing moment AB, which is this one, going in anti-clockwise direction, is minus WL over 8. Then fixing moment BA, in clockwise direction is equal to plus WL over 8. Then the second case, we go to the second case. The second case, this is a beam, as you can see. It is a fixed beam with 2 supports and loaded with a UDL of magnitude W over M. So we have this moment going in this direction, it is moment B, and this moment in anti-clockwise direction, moment A. So fixing moment AB is equal to minus WL squared over 12, this moment. And then fixing moment BA, this one, is equal to plus WL squared over 12. A third case, as you can see, is again a 2 support beam fixed at both ends, loaded with a load W, and this one is not at the center. So it means it is a centrically loaded beam. So it is loaded at A from this side and B from this side. So the fixing moment AB, this moment, is equal to minus WAB squared over L squared. And then the fixing moment BA, this moment, the formula is this one. This is another case. It is a fixed beam on 2 supports, but it is subjected to a moment at the center of the beam, which is L over 2, L over 2. And this distance from A to B is L. So fixing moment AB is equal to M over 4, is also equal to fixing moment at BA, which is equal to M over 4. Another case is again beam subjected to a moment, but not at the center. So the moment is eccentrically placed on the beam at distance A from A and at distance B from B. So the distance from A to B is L. So fixing moment AB is equal to MB over L square into bracket 3A minus L. And then fixing moment BA is equal to MA over L square into bracket 3B minus L. So this is the last case. This is a beam with a UVL loading, uniformly varying load. So the fixing moment at AB is equal to minus WL squared over 30, this moment. Then fixing moment at BA is equal to minus WL squared over 20, so this one. So we will come to see how we will be calculating this fixing moment when analyzing a beam or a frame requiring moment distribution method. Application of moment distribution method. Application number 1. Moment distribution method is used in the analysis of continuous beams with fixed ends. Application number 2. It is used in the analysis of continuous beams with simply supported ends. Number 3. It is used in the analysis of beams with overhanging ends. Then number 4. Continuous beams with coupling or turning effects. And then number 5. It is used in the analysis of simple frames. This is an example of simple frames. And then the last one, analysis of Portal frames. frames. So this one is an example of a photo frame. So we will analyze each of them from number 1 to number 6 using moment distribution method. So stay tuned for more updates from Odavig Structure Hub, and comment, like, and share my videos. So we meet again in my next session. Thank you for your time.